All right. Hello, everybody. Welcome to the notes video on shadow zones and all the different scales that we use to measure different things about the earthquakes. These notes start at the bottom of page 2 in your notes packet, so make sure that you're filling in your notes, answering the questions in the video as they come up, submitting this on Edpuzzle, and turning it in on Google Classroom. So, the reason I had you all do that graphing seismic waves activity was so that you could model what real life scientists have done, in that they've analyzed and looked at how P and S waves travel through the Earth to help them come up with a working model of the different layers of the Earth. They could see that the P waves traveled through all layers of the Earth, but the S waves stopped when they reached the outer core. And remember, S waves travel through solids only. So if they aren't traveling through the outer core, this allowed them to infer that it was a liquid. So our current model has liquid, the outer core is the only liquid layer, and all of the other layers of the Earth are solid. It just may change the composition a little bit, as you saw with the fact that the P wave did not go all the way through at a straight line. All right, what this creates though is something called the shadow zone. This is an area that does not experience any type of seismic waves. And it is a result of both the S waves being stopped by the liquid outer core and P waves being bent or refracted by the liquid outer core as they travel through it. So if you look in this picture on the left, the pencil appears to be broken a little bit as it's sitting in the water. But that's really the water diffracting how and changing how the light bends to see the pencil. And so we see it at a different angle compared to what it actually is. And that's kind of what's happening in the earth. If you look at the picture on the right, as the lines are traveling through the core, they don't go in a straight line. They bend a little bit as they go from the mantle to the outer core, or a little bit from the outer core into the inner core. And this is a more close up showing each individual type of wave. P wave is on the left, S wave is on the right. And the whole opposite side of the Earth on the right does not receive the S wave, based on the fact that any that would be going straight through the Earth are going to be stopped by the outer core. Whereas the P waves do travel, but they bend, and that bending creates this region where no seismic waves are detected. So we'll talk about this more in class, and I'll show you some pictures of what this overall looks like. All right, so how do we measure earthquakes? There are two values that we look at. The first is magnitude, which is how much the earth actually shook. So what was the energy required? What's the strength of the earthquake? And what's the intensity? What is the damage done by this earthquake? So we have different scales that we can use for this. The Richter scale possibly is the one that you've heard of the most, and this is the one that was used by a lot of scientists, but in the last 20, 30 years or so, we have shifted away from using it. It is a way to measure the magnitude or the energy of the earthquake, and each value on the Richter scale is 10 times greater than the value before, meaning a value of 2 is 100 times greater than a value of 1. But scientists don't commonly use this anymore, and I'll explain in a minute why that is. So this is a rough picture showing the increasing amount of energy equivalent to an increase on the Richter scale. Typically, lower values are more common, higher values are less common. The moment magnitude scale is what is actually the preferred measure of magnitude, because it looks at a lot of different things that the Richter scale didn't. It looks at the amount of energy released. It looks at how much of the fault moved. It looked at how much force would be required to move that. What type of rock was affected? It's going to take a lot more energy to shift granite than it would shale. Shale is a very soft rock, so it's not going to take as much energy to create an earthquake with that than it would a harder rock. Each step is still 10 times stronger, but it doesn't really have an endpoint. We've just only gotten up to 9.5 that we've recorded. That's not to say we can't go higher. We just haven't recorded one, and I'm perfectly okay with that. So you have this in your notes as well. This is just kind of showing uh, energy equivalents also. And we have about million value 2 earthquakes every year. Um, we get less common with the 9s and the 8s. I would say recently some of the strongest earthquakes have been in the 7 range if we've had large ones. The last 9 that I can remember was the Japan earthquake in 2011. Not to say haven't been others, it's just that's what I remember off the top of my head. The final scale that we can use is the modified Mercalli scale. This measures the intensity of the earthquake by looking at the damage associated with it. There are some problems with this because the amount of damage can be subjective. How I interpret the damage might not be how you interpret the damage. And the damage can be affected by the distance from the earthquake epicenter, the type of rock. Again, if you're close to the epicenter but you're made out of loose sediment, the ground's going to shake a lot more than if you have solid bedrock. And whether building codes have actually been enforced in the area. If you live in an area that does not have strong building codes and a small earthquake hits, there could be a lot more damage than if you live in a suburban area or an urban area that does have stronger building codes. So, to me, the modified Mercalli, other than mapping out the damage done, is not the best scale. I go with the moment magnitude scale because it looks at a lot of different things that are being affected. But, you know, it is what it is. And so here is a quick abbreviation of the modified Mercalli scale. We rank this on a scale of 1 to 12. The Mercalli values are on the left. Those are the Roman numerals 1 through 12. And you have a description for each of the categories. Like modified Mercalli value of 1 is detected only by sensitive instruments. And on the right, it kind of gives the magnitude equivalent from a Richter scale. So like a 1 might be up to a 1.5 on the Richter scale. A 3 on the Mercalli scale is going to be felt indoors, but not always recognized as an earthquake. Standing autos could rock slightly, and it's kind of like a passing truck. I would say this is what I have experienced for my earthquakes is that I'm in like the 3 damage zone, but it was probably worse the closer you were to the epicenter. You compare that with like Mercalli value of 10, which is the X. Most masonry and frame structures are destroyed, the ground is cracked, rails are bent, and there are landslides. So the higher the Mercalli value, like if you look at 12, which is the XII, damage is total, waves are seen on the ground surface, and I'm not talking about waves of water, I'm talking about the ground looks like it is moving in a wave. Lines of sight and level are distorted, and objects are thrown up in the air. So the higher the value in the Mercalli scale, the stronger the damage, and the closer you are to the epicenter. So that's where the Mercalli scale can come in handy, is if you don't know where the epicenter is, you look for the areas that you have the reports of the most damage. Those areas are closer to your epicenter. All right, answer your last question and submit it on both Edpuzzle and Google Classroom.